Ah, hi. I believe everyone can hear me right now. Ah, hi. I believe everyone can hear me right now. So, hi. Let's begin talking about this. Oh, I'm gonna. It's my first time doing all these configurations, so that is my fault. But anyways, hello everybody. Today I'm gonna be talking about some basic control, feedback control stuffs, and I'd like to um, go through some actual examples and try to apply discuss now. Okay, so let's begin. Do this. All right, so if we want to describe a system, it can be a physical system or anything, and we want to make a mathematical model of it. There are several ways to represent a particular system mathematically. One of the most widely accepted form is called state space form. So state space form, I'm just gonna write down the standard form of this. So this system of linear equation is basically a standard form of state space form. And here, by the way, these underlines down there indicates that those are vectors. Those are vectors. So they can be any n by 1 column vectors. Right, and here x is called a state vector, and it has every information about the system in it. So, for example, think of a system like spring damped spring mass system. I'm just gonna redraw this. So, suppose we have a system that looks like this. A mass of m is attached to one end of the spring with a spring constant k and a damping constant b. If we impose some certain initial condition, say x naught, then the thing will show behavior that will look something like this. Right? It's gonna oscillate. The first characteristic of this plot is one, it oscillates, and two, um, it decays exponentially. So in order to fully characterize the system that behaves like this, that shows behavior, something like this, we gotta define the state vector. In this case, the position denoted by x and velocity denoted by x dot comprises our state vector x. So if we have information about these two quantities, then we can fully define the system, and furthermore, we can mathematically anticipate what's going to happen in the very next moment of time. Mm, right. And also, U is input vector. This one is called input vector, and this thing is uh, some something that we can actually take control of. For example, a motor or applied force, stuff like that, and things that we can actually change and uh, modify. So this thing is directly related to actuators. We want to change the state of any system through actuators such as DC motors or other things. And the effect of those actuators are included as this U input vector. And Y is output vector. This thing is what we want to uh, control. Mm, okay, let me put this in this way. U is something that we can control, and Y is something that we want to control. So this thing, this Y is something physical and something tangible and something sensible that can be sensory sensors. This is a real existing physical uh, stuff, which can be detected by sensors. For example, position can be our output, angle between angle from some reference line can be another output, velocity can be our output, and so on. And we got A, B, and C, and D. Those are all matrices. These are all matrices. And for linearly time invariant system, we have uh, constant coefficients for all these four matrices. A, B, C, D are constant coefficients. And by linearly time invariant, I mean the system does not change as uh, time changes. So this is one way of defining our system. And another way of um, characterizing the system is making use of differential equations. So we can put things into differential forms. For example, there can be first order diffie and second order diffie. First order in canonical form looks like this: tau times y dot plus y equals k times u, where tau is a time constant, um, and k is a DC gain. DC gain means in steady state, our first order C system's output, y in this case, is going to reach the value of k. And this canonical form of second order linear system is something that looks like this. We've got a y double dot here, and we have 2 times zeta times omega n times y dot plus yn squared omega n squared times y equals omega n squared times u. So same as before, we have y as an output and u as an input. And zeta right here and omega n, those two are key coefficients because the behavior of the second order system is gonna be determined by the relative value of these two. For example, if zeta is uh, between the value 0 and 1, we're gonna have a damped oscillation, and, and for other zeta values, uh, we're going to be observe some other behavior of the system, like critically damping or overdamp or other stuff. All right. Usually, in um, most of the things that happen in this real physical world can be described either in first or second order DQs. Okay, so this is another way of describing the system. So if you want to make use of this differential form and express everything using differentiation with respect to time, then we have to be able to come up with these coefficients like tau, k, zeta, omega n, and things like these. But times figuring out these numbers can be very cumbersome and tedious because everything here is written in time domain, right? Even though not written explicitly, these dots and double dots indicate that these variables are uh, functions of time. So that is why we can take derivatives with respect to time. So people came up with some revolutionary method of uh, finding the solution of these kind of differential equations, which dramatically facilitated uh, the calculation time. That's called the Laplace transform. So this Laplace transform basically transforms, it maps a function which is expressed in time domain to a Laplace domain. The strongest power, the most powerful feature of this Laplace domain, and the main reason why people are using this Laplace transformation is that um, derivatives and integrals in time domain can be expressed in polynomials in the Laplace domain. For example, the operation of taking the time derivatives becomes multiplying by s in the Laplace domain, and taking integration, doing the integration with respect to time becomes dividing by s in the Laplace domain. So if it, um, um, in this way, we can easily figure out and characterize the system more easily. So let's take a look at, uh, for example, if we take this second order equation, differential equation that I just discussed. So for now, this equation is written in time domain. And we would like to change everything into Laplace domain. So we can take a Laplace transform of this entire expression. I'm just going to copy and paste anything. Yes. And what's going to happen? We have y double dot, which is equivalent to multiplying by s squared because we differentiated twice. So we got s squared times y. We denote uppercase of y to indicate that the lowercase y that was expressed in time domain is now converted into the plus transform of that. Okay. And the second term, the constant just remains constant. So we have these constant coefficients unaltered, but we have another time derivative over there, which becomes s, right? Because we're taking time derivative only once. Then we got another y right here. Okay. Similarly, omega n squared is another constant coefficient, so that taking Laplace transform doesn't change anything about this. And we do have this y in Laplace domain, and that entire thing becomes equivalent to what? Omega n squared times u, the uppercase u. Because u is also a function of time. It can be a function of time. So if we take the Laplace transform, it's going to change its form. By the way, Laplace, I'm going to write down the mathematical definition of Laplace transform. So suppose there is a function called x of t, and if we take the Laplacian transform, we denote by this, we put a curly bracket around this x of t, and then we have this s right there, equals, we take the integral from 0 to infinity of what? X of t times e to the negative st with respect to the smaller amount of time slice dt. Down. So if we change the value of s, by the way, s is a complex number, which means in general form, s can be expressed as sigma plus I times omega. So we have real part and imaginary part for s. So in the end, what we want to do is we want to express the result of the Laplace transform of any time domain function in the complex plane, where we have real axis instead of x as a horizontal axis, and we got imaginary axis right here. So we want to see, we want to vary this s by changing the value of sigma and omega. If we make sigma bigger, then the effect will be traveling rightward, right? And if we increase omega, then it would have the effect of traveling upward in this complex plane. Okay, so that's what we want to do in the end, and we want to figure out how the characteristic of the system uh, by expressing by mapping the time domain function into the Laplace domain function. Let's see. Okay, so we can rearrange what we have here. We can factor out y of s, and we're going to be left with y of s times s squared plus 2 times zeta omega n plus omega n squared. That's equal to what? Omega n squared times u of s. Right. And reorganizing everything in terms of ys, we have y of s equals to omega n squared divided by this entire expression in this parenthesis times u of s. And this thing right here is called the transfer function, and often denoted by g of s or p of s. It's called the transfer function. It's called transfer function because what it does is that when multiplied by the input in the Laplace domain, this function gives the resulting output function in the Laplace domain because it actually transfers the input signal to output signal. That's why this is called transfer function. And by the way, this transfer function is uh, this has a form of convolution integral in time domain. Um, okay, let's suppose that H here is the impulse response of a system, and U of t is an arbitrary input. What we do here is that we're taking the convolution integral of these two. So basically, it has the effect of accumulating the impulse response. Wait, so let me say this thing a bit better. So first, we can express any arbitrary input signal as a sum of delta functions, which is impulse function. And for each of them, we calculate the response, the impulse response function. And we take the convolution of those two, the impulse response and arbitrary input vector, arbitrary input function. And what it does is that uh, the effect of each of those slices, each of those um, impulse functions will be accumulated and will be added. So we're kind of like superimposing the effect of each of those impulse functions. So that's what's happening inside this transfer function. Okay, once we define transfer function, what we can do is we can find out the poles. So poles are basically defined as the denominator of this transfer function. Sorry, it should be are the zeros of the denominator of the transfer function. Why is that? Because if we put 0 into the denominator, then things will explode. Like they will go to infinity. It means for that, at that point, for that frequency and for that exponential decay property, the system's gonna this. So the system's typical behavior can be characterized by those two quantities. One, its frequency, and two, its exponential decay. And if we um, maximize this transfer function, if we find the singular point of transfer function in the Laplace plane, it is equivalent to finding out the the most characteristic point. So this frequency and this exponential decay are going to uh, best characterize the system, the behavior of the system. The idea. Okay, so in this case, we're gonna have s squared plus 2 times zeta times omega n plus omega n squared equals 0, and we can just use our famous formula to find out the zeros of this polynomial equation. gonna be negative zeta times omega n plus and minus omega n. I just factor out omega n squared out of the square root and it became omega n because we're gonna have omega zeta squared times omega n squared, and we're gonna have negative omega n squared again. So I just factor out omega n and then put the thing, extract the thing out of the square root. So as I mentioned before, for the value of theta that lies between 0 and 1, we're going to have something negative in this square root, which means S will become complex, sigma plus I omega n, right? And this I term has the physical implication of oscillation. Because what we did back here is that we multiplied things by e to the negative st, and what does e to something imaginary imply? It implies that um, so if we ask to our friend Euler, then the implication of having an imaginary exponent is having a combination of sines and cosines, right? Right. So that's one implication. And if we have something positive inside the square roots, then we definitely won't gonna have the oscillation behavior. Look, all of those things are defined by these coefficients, like theta and omega n, as I mentioned before. Okay. Now we're actually going to try some. Let's try some examples. Here goes our first one. Suppose there's a system that is described by the following differential equation: y dot plus 9 times y equals 5 times u. So we want to find the transfer function of find transfer function. Okay. So what we have to do first is that we have to change everything and express everything in Laplace domain. So we take the Laplace transformation of this entire equation, and what we're gonna have s times y of s plus 9 times y of s is 5 times u of s, right? And then we factor out ys. I'm just gonna divide both sides by s plus 9 because it's kind of obvious. So what we have here is our transfer function. So it's very easy, right? And we have our second problem here, y double dot of t plus 6 times y dot t plus 25 times y of t equals 2 times u dot t plus 9 times u of t. Again, we take the Laplace transformation of this entire equation and we're going to be left with s squared times y of s plus 6 times s times y of s plus 25 times y of s equals 2s of us plus 9 times us. And if we factor out ys and divide both sides by the whatever we have multiplied to y at y of s, we're gonna have something like this: squared plus 6s plus 25 goes to the denominator, and what we have up there is 2s plus 9. Okay. So again, this term here multiplied to u is our transfer function. And let's take a look at our final example, which is y of t plus kp. This kp stands for the proportional coefficient. Proportional coefficient multiplied to our input plus this is integral coefficient. Why is it called integral? Because it is multiplied to our input, the integral of our input. And lastly, what's going to be the last one? It's sort of obvious that the only remaining thing must be the derivative, and also it can be easily seen that this kd, the derivative coefficient, must be multiplied to the time derivative of u. Okay, again, let's take Laplace transformation. Y of s equals kp times u of s plus what's gonna happen if we integrate in time domain, in Laplace domain? Like taking derivative is multiplying by s, so taking integration is dividing by s, so we're gonna have 1 over s here, ki times u of s plus s times k of d times u of s. Rearranging, we have y of s equals to kp plus reciprocal of s times ki plus s times kd, factor out us. So transfer function in this case is going to be this thing. Very straightforward. Right? Okay, now let's take a look at the PI control. Suppose we have a plant that does um, this operation to the given input. So the input goes in like this and comes out the output. And let's say our reference point is given as R, and we want to do a feedback closed loop control. So the the sensed, what should I say? The sense value, the output that is sensed through the sensors is feeded back to the input. And the difference between the desired reference value and this current value, the current number, is compared, and we subtract what we have for now from our desired value. And what's gonna be left? We're gonna have an error, because error is defined by the difference between what we want and what we have. Okay? And first thing we do is we multiply our error by the proportional constant. And also we take an integration, and remember everything is expressed in Laplacian domain. So instead of explicitly writing the integral sign, we just divide it by s. And the thing goes here. So what we want to do is find out the transfer function that brings r from y. Let me just write everything in uppercase just to indicate that we're in Laplace domain. Let's first take a look at this portion. So we can write down the relationship between u of s and y of s that goes like this. Y of s equals k over tau s plus 1 times u of s, right? And what is u of s? U of s is a linear combination of kp times the error and ki over f times e, the error. Okay. We have u of s equals kp times, sorry, I'm just gonna factor out this error, okay, plus ki divided by s multiplied with e of s. And lastly, if we take a look at this portion, our system configuration, we're gonna have e of s. We can find the expression for this e of s, which must be basically the difference between r of s and y of s, where r indicates the desired point, the reference value, and y is our current sensed value. Alright, cool. So now it's all plug and play. So from this expression here, we can substitute u of s by this expression that we just calculated. And then lastly, we can use this expression here instead of the error. Okay. Now let's try to expand this things just to make the equation clear. What are we gonna have? Let's just say we're gonna find the common denominator to be s times tau s plus 1. We have k times kp times s, correct? Because it didn't have s. This kp term didn't have s in the denominator. So we have k times kp times s plus k times ki multiplied by the difference between r and y. So what we want to do here is that we're gonna have this entire thing multiplied with negative y of s. We want to put this thing to the left hand side. Then what are we gonna have? Y of s is going to be 1 plus this entire thing here, correct? That is what? Okay. So what now? We can divide both sides by this expression here. It's easy. We all learned this kind of procedures in kindergarten. So this is what we have. And our, let's go here. So I'm gonna get rid of this redundant 1 here. Doing operation like this. Plus this thing. Makes sense, right? Why did I do this? Because I want to get rid of these denominators from both sides. Looking good, right? So in this case, this is our transfer function because this expression here, when multiplied to our input reference value, gives us the resulting y. So our transfer function, in this case, must be what we have here. It was easy. Mhm. Okay, now let's take a look at another type of problem. So as I mentioned before, there is several ways to express a certain mechanical system, one of which being the state space form. And state space form operates in a way that is similar to the transfer function. The only difference is that we're doing the calculation in time domain, the Laplace domain, but still we can make use of the block diagram when we want to express the how our plant or transfer function uh, actually transfers our inputs to the output. So it will look like this. Suppose we have an input that looks like this. Input is given by R, and this R will be put into as an input to our to the state space form. The standard form of state space form look like this: x dot equals a times x plus b plus u, where x is a state vector and u is an input vector. So this equation here tells us how the system will change as time goes. Okay? So for a given state and for a given input, it tells us how the system will behave the very next moment. And we want to calculate the output using these two values as well. So in the end, we want to calculate this y. After all these procedures, tedious computations, we want to calculate the output because that's something sensible and that's something we want to control. Let's suppose x is a vector, 2 by 1 vector, where the first element is x1 and the second one is x2. Um, let's say there is a system that can be characterized like this. So we have, um, these are all scalars in this case. These are not vectors anymore. We can compute x1 from these relationships, and then y1 is another input for the second state space form. So R was our first input, and Y1, which is the result of the computation of the first plant, is the second input for the second state space form. We're going to have X2 and U2s here, and we have Y2 as our final output. Let's write down some key relations. I'll just copy and paste what we have here and substitute known values. Like, for example, we can put R in place of U1, and then here we can use Y1 in place of U2, but at the same time we already know that Y equals this expression right here, Cx1 plus Du1. This is and we know that Y2 must be Y because that's our final result, right? So combining these two, we want to express everything in terms of this single plant, okay? So we have x dot vector there. What is x dot? X dot is x1 dot and x2 dot. That's a vector. I'm just gonna copy and paste what we already have over here. It's gonna look like this. And we want to express things in linear combination, in the form of linear combination of x and u. Something times x plus something times u. Okay. So we have x1 here, but no x2. And also with r. Instead of u1, I'm going to use r because we want to relate r and y in the end. And we have b times r. And for the second row, we have b times c as a coefficient of x1, and we have a as a coefficient of x2. And also we have b times d. Yeah, so it's basically done. And what's y? Y in this case? Y must be y1 and y2. Again, I'm just going to copy and paste stuff like this. And we write everything in linear form. Again, we have c multiplied to x1, but we don't have any x2 term here. We got d, and what about here? We got d times c and C, and we got D times D. Is it correct? Not sure. Let me go do the calculations real quick once again. Um, Sorry, these ABCD matrices and ABCDs are different. These are different numbers. So we have 2, 2, and since this thing came from the first plant, we have 1 and 1. And Y2, we have 2, C2, and D sub 2. And we again, we have C sub 1 and D sub 1. Okay, 1, 1, 2, 2, 1, 1. Okay, open that. Gonna erase all these and right. And copy and paste all these. Like this. A1, 0, B2, C1, and A2 plus B1 and B2, D1. Okay, and for Y, another copy and paste. What are we gonna have here? C1 goes here, 0, B2, C1, and C2 for X, and we have D1, D2, D1 for R right here. Alright, cool. So this is our final sketch. So for given R, we're going to have something that looks like this. Okay, cool. Now let's do something similar for the feedback interconnection. So this time we have some similar configuration, but the difference is that instead of having the plants in series, we're going to have them in parallel and not a regular parallel connection we're gonna feed this entire thing back all the way to here. Okay, so here we have r, and we should subtract this, the result of this transformation, which is y2, from r, which gives us the error. Okay, and this error is feeding into this actuator, so we can say that u1 equals that value. And what comes out of that is y1, which is y in this case. So y1 goes in here as u2, and y2 comes out. Okay. All right, let's begin. So the error is defined by r minus y2. Similarly, let's just copy and paste what we have here. So here, instead of u1, what do we have? Error, right? And error is defined by r minus y2, correct? Here also, instead of u1, we have r minus y2. Sorry, we don't have this term here. Okay, gotta erase. Okay, and at the same time, we have this expression in which we have u2. We already know that u2 is y1, and y1 is c1 times x1. Instead of u2, we're gonna put c1 x1. Instead of u2, we're gonna put c2, c1 x1 again. And I'm gonna replace y1 by y because that's what we want in the end. And what's y2? Y2 is again what we have here, correct? Now all we have to do is rearranging these things into a linear combination of input and state vector. And just rewrite the things here. Okay, got A1 minus B1 times D2 times C1 of x1. We have negative b1 e2 x2. And we got this remaining b1 times r. Alright, yeah, we're ready to go. So again, we have x dot equals x1 dot here and x2 dot there. And again, just copy and paste. And rearranging things. We have this term minus b1c2, b2c1, and a2 multiplied to x, plus we have b1 that goes up here, and we got no r related terms down there, so this is our b matrix. And we have y equals y1, y2 that equals to this one and this one. Okay, so we have c1 0, d2 c1 c2 times x plus 0 times r. Does this thing looks reasonable? Because y is 1 times x1 and y2 is, it doesn't contain any r term in it. So it looks like makes sense. Okay, let's rewrite things. So again, if we want to express everything that looks like this, we're gonna have something like this. And here we have an expression for x dot as well as that for y. Yeah, it's nice. We also have this. Alright, that concludes our example. For joining me tonight, and hopefully we can see you guys later. Thank you.